We are once again continuing with our last topic in physical chemistry, which is electrochemistry. In our first lesson on this chapter, which is the last topic in the physical chemistry of A level, was modes of conduction of substances. I looked at that in detail, where I looked about metallic conductors and electrolytic conductors. Then we looked at the common terms in electrolysis. The common terms we looked at, we specified the term electrolysis itself. We looked at the term electrolyte, what an electrolyte is. We looked at what strong electrolytes are. We looked at what weak electrolytes are. We looked at what non-electrolytes are. We also went ahead and looked at ionic electrolytes and also covalent electrolytes and the mode by which they conduct electric current. We went ahead and looked at what we call electrodes, where we in details defined what an anode is and what a cathode is in electrochemistry. We went ahead and saw the changes that take place during electrolysis. We also looked at what we called selective discharge of ions and the factor that affects selective discharge of ions. I hope you remember the three factors. One was position of the ion in the electrochemical series. The other one was nature of the electrode used. And we also looked at concentration of the ions in solution. I strictly specified ions. We saw nature of electrode, where we looked at effect of a mercury cathode in electrolysis of concentrated brine or sodium chloride, and effect of the copper electrode during electrolysis of copper to sulfate solution. Those are the most important electrolytic processes you have to recall. Position of ion in the electrochemical series, we looked at that in detail. Concentration of ions, we looked at concentrations of electrolysis of conc sodium chloride or conc hydrochloric acid versus electrolysis of dilute sodium chloride or dilute hydrochloric acid. And we were seeing what really happens at the anode. Whereby we said that chloride ions are discharged in preference to hydroxide ions, which come from water. Although the solutions have water, chloride ions are discharged in preference to hydroxide ions due to a high concentration of the chloride ions in concentrated sodium chloride. I hope you do remember that. We said although the hydroxide ion is lower than the chloride ion in the electrochemical series, it won't be discharged by the chloride ion. I don't want to go into the details of that previous lesson. I want us to straight look at laws of electrolysis. One good man that was called Michael Faraday. I know most of you have heard of Michael Faraday. Michael Faraday took a lot of time to study electrolysis, electricity, and electrolytes. And he formulated two laws, which we are still using up to now. He called them laws of electrolysis. In his first law, in Faraday's first law of electrolysis, he said that the mass of a substance liberated at an electrode, it can be the anode or cathode, liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. That's what Michael Faraday formulated as his first law. He said that the mass of a substance liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. If you're electrolyzing copper 2 sulfate solution using a copper anode and a copper cathode, you're electrolyzing that solution, copper 2 sulfate solution. The quantity of electricity will pass through this electrolyte here, the copper 2 sulfate solution, will determine the amount of copper that will be deposited at the cathode. Because you know in this experiment that copper 2 ions in solution get deposited as copper metal at the cathode. They migrate to the cathode and get deposited there, as long as you are using copper electrodes. So the mass of copper that is deposited is directly proportional to the amount of electricity that you pass through the electrolyte. So the higher the amount of electricity you pass through the electrolyte, the more the copper gets deposited. The lower the amount of electricity you pass through the electrolyte, the lower the mass of copper that gets deposited at the cathode. What's the mathematical implication of this? If M represents mass of substance deposited and Q is representing quantity of electricity, then the mass of the substance deposited is directly proportional to the quantity of electricity Q. But from your physics, you are aware that Q is equal to I times T, I being electric current in amperes, and time, T being time in seconds. Are we together? So you are aware that Q is equal to IT. What does this imply? This implies that M is directly proportional to IT. When you remove the proportionality sign, you will introduce a constant here, which constant becomes a letter E. This constant that we introduce here is called the proportionality constant. If you don't call it the proportionality constant, you can call it the electrochemical equivalent. You can call it the electrochemical equivalent. We began from the law itself, where we're saying mass of substance deposited at an electrode is directly proportional to quantity of electricity. But quantity of electricity is the product of electric current in amperes strictly, and the time in strictly seconds. So when you equate this and remove the proportionality sign, a constant is introduced, a constant E, which we are calling the proportionality constant. That is Michael Faraday's first law of electrolysis. Michael Faraday was not settled, as if that was not enough. He also devised a second law of electrolysis. And in his second law, he came up with a law saying that, I'm calling it Faraday's second law of electrolysis. In Faraday's second law of electrolysis, he said that the quantity of electricity required to liberate 1 mole, quantity of electricity required to liberate 1 mole of any element is proportional to the charge number of its ion. That is Faraday's second law. That the quantity of electricity required to liberate 1 mole of any element. The element can be aluminium, it can be hydrogen, it can be chlorine, it can be any element, it can be sodium, it can be any element. Required to liberate 1 mole of any element is proportional to the charge number of the ion formed by that element and the corresponding charge it has. What do we mean by this? Or what did Faraday mean by this? He denoted the charge number on any element by a letter Z. If the charge number is Z on any element, this charge number can be positive or negative, depending on the element. For example, for the hydrogen ion, Z is positive 1. For the aluminium 3 ion, Z is positive 3. For the chloride ion, Z is negative 1. For the oxide ion, Z is negative 2. However, in our calculations, we shall take the magnitude of Z always. So if Z is positive 3, we shall always take the magnitude and take it as 3. The magnitude of Z is magnitude of negative 2. We shall take Z as 2. We shall not take the sign as we are dealing with the calculation. So that is Michael Faraday's second law, which is said the quantity of electricity required to liberate 1 mole of an element is proportional to the charge number of its ion. So he didn't stop there, but he classified that Z. Should note that Z is always equal. Actually, the magnitude of Z is always equal to the number of moles of electrons. Z is the charge number. It's always equal to the number of moles of electrons required for the ion to be discharged. For example, if I'm discharging an aluminium ion from aluminium metal during electrolysis, I balance this by 3 electrons. So you realize that the number of electrons required to discharge 1 mole of aluminium is equal to the charge number Z. That's what I mean by this. 0 is equal to the charge number. So Z0 is equal to number of electrons. And this equation here has a lot of information that we are going to extract from it. And we shall be using that information in calculations. What is the first information we are getting there? The first information is that Z is equal to 3. The second information is that number of electrons. Actually, I will say that, look at this. 3 moles of electrons are required to discharge 1 mole of aluminium, 3 iron. That's the other information I'm getting from this same equation. The number of moles is always equal to the number of Faradays. So this implies that also that 3 Faradays are transferred a Faraday is a measure of electric current also. So 3 Faradays are transferred for discharge of 1 mole of aluminium 3 iron. However, I want you, dear students, to note that 1 Faraday, you should know this, is always equal to 96500 coulombs. So 1F is equal to 96500 C. What does this imply according to the equation? It implies that 3 times 96500 coulombs are transferred for discharge of 1 mole of aluminium 3 iron. Allow me convert the mole to mass. You are aware that aluminium is 27. So that means these columns are transferred for discharge of 27 grams of aluminium 3 iron. Let me hope you understand this.
Yes, teacher.
The other thing I want us to note is that 1 mole of electrons, 1 mole of electrons is equal to Avogadro's number, 6.02 times 10 power 23 electrons. That's what we call 1 mole. If you see 3 moles of electrons, then that means those 3 moles have 3 times this number of electrons. So if I want this in terms of electrons, I will say 3 times 965 times this figure of electrons are transferred for discharge of 27 grams of aluminium. I'm getting about a lot of information from this equation. And that information is going to be very useful to me in case I'm doing calculations. So which other information do I have? These are 3 moles of electrons or 3 Faradays. Each Faraday having that amount of charge in terms of coulombs. So if I want total number of electrons, it will be 3 times 96500 times 6.02 times 10 power 23 electrons are transferred for discharge of 27 grams of aluminium 3 iron. So that has been a by the way. And you should use that by the way for some calculations, as we shall later see. The next bit of Faraday's laws is to determine what we call the Faraday's constant. We have just seen that 1 Faraday is 96500 coulombs. This is what we call the Faraday's constant. This value here is what we call the Faraday constant. Which experiment can we carry out to determine that that's really the Faraday constant? That's our next point of consideration. It's what I want to see here. I'm calling it experiment. It's not a common experiment, but it's part of our syllabus. So we need to know it. You never know. Experiment to determine the Faraday constant. And we want to get the Faraday constant by electrolysis of copper 2 sulfate solution. By electrolysis of copper 2 sulfate solution. Let's try to see how is this experiment carried out. I'll first of all draw a setup of the apparatus that we are going to use for this particular experiment. I have my DC source. That is my DC source. The longer terminal is the positive terminal. The shorter one is the negative terminal. So this is my DC power supply. DC means direct current. In this experiment, I need a variable resistor. This is what I'm calling a variable resistor. In the same experiment, I need an ammeter. I need an ammeter. So this one here becomes my anode. And this one becomes my cathode. This is the anode. And this is the cathode. Lastly, I need what we call the electrolyte, which electrolyte in this case is the copper 2 sulfate solution. What's the theory behind this electrolysis? The theory behind is that this electrolysis that we electrolyze in copper 2 sulfate solution. In copper 2 sulfate solution, we have copper 2 ions and sulfate ions. We also have hydrogen ions and hydroxide ions. I've forgotten, but we shall use copper as electrodes. We should use a copper anode and a copper cathode. We have already seen what happens during this electrolysis. These ions here migrate to the cathode, and these ones migrate to the anode. At the anode, the sulfate and hydroxide ions, none of them will be discharged. You are aware of that. We looked at that factor which we call the nature of electrode being used. The hydroxide ion would be discharged if this was a graphite electrode or a carbon electrode. But since it's a copper anode, none of them gets discharged. Instead, the copper anode dissolves and it goes on decreasing in size. To form copper 2 ions, this solution remains blue. Are we together? Then at the cathode, copper ions and hydrogen ions migrate. When they migrate there, the hydrogen ion is not discharged due to the nature of the electrode, but instead the copper is deposited. I think here the knowledge of electrochemical series comes into play. Which ion is lower than the other in the electrochemical series? The copper 2 ion. So the copper gets deposited at the cathode. We shall have a layer of copper getting deposited here, and the anode will go on decreasing in size, okay, as it is dissolving. So that theory, we shall measure the mass of copper deposited here and the amount of electric current used, which is measured by the ammeter, and use Faraday's laws, which I've already seen, to get the Faraday's constant. So what is the procedure of this experiment? The procedure is that arrange the apparatus as shown. Arrange the apparatus as shown. That's the first thing. Then secondly, you should tell us the use of the variable resistor there, because it's not common in most of the experiments. You should tell us why it is there. It is there to keep the current constant, because you want a constant amount of current, the amount of current constant. You want a constant amount of current to be passed through the electrolyte, such that you get accurate results. We should weigh the mass of pure copper anode. Remember, the anode is going to dissolve x1 grams, and pure copper cathode y1 grams separately before the experiment. We need to know the mass of each separately before the experiment. Are we together, dear friends?
Yes, teacher.
Swabla, or is somebody joining here? Okay. So we should weigh the mass of the pure copper anode and the pure copper cathode separately. Then what we did next is to pass electric current. Pass a constant electric current. Pass a constant electric current. We shall call it I amperes for a given time interval. In brackets, t seconds. Take some time. Pass electric current, which is a constant. That's why there is a variable resistor here, to keep the amount of current passing through the circuit constant. So you pass a constant electric current for a given time interval, can call that time t seconds. So after that period of time, the copper anode will have to dissolve and some copper will have to get deposited at the cathode. In other words, at the anode, what happens? At the anode, so long as you're using copper electrodes, the anode dissolves to give us copper 2 ions. That's why the solution remains blue, doesn't fade in color. Then what happens at the cathode? At the cathode, the copper ions that have dissolved from the anode, and even those from the solution, get deposited there as a layer of copper metal. So that's what will happen at the end of the experiment. And it implies that the overall reaction in this kind of reaction, it is copper plus copper 2 ions, still giving us copper metal and copper 2 ions. So the overall reaction is an exchange of copper 2 ions at the end of the experiment. Okay, now, if you have known what happens, we have known what happens at the anode and what happens at the cathode. We are going to remove our cathode and anode at the end of the experiment. Remove the cathode and anode at the end of the experiment. Wash them with the propanol, an organic solvent. And after washing them with propanol, then dry them and then weigh each again separately. So what do? We remove the cathode and anode and wash them with distilled water. Why do we wash them with distilled water? We want to weigh the exact mass of the electrode and its contents, whether copper is deposited there or whether it has dissolved. Wash them with distilled water and then propanol. And dry them. However much we want the mass of n of these, it would be good to measure the mass of the anode where copper is deposited and the mass of the cathode, sorry, where copper is deposited, than the mass of the anode which dissolves. Because the anode, I think we should measure the mass of the anode. Yeah, let's measure the mass of the anode. Because copper does not stick well to this cathode here. We need to know the mass of the anode that has dissolved. When we measure the mass of the cathode, copper doesn't easily stick well. It may stick, some may still fall off and gets at the bottom of the beaker or the container through which the experiment is done. So it's better we measure the mass of the anode. It's preferred that we measure the mass of the anode because copper does not stick well at the cathode. So what shall we say? We shall now say weigh the washed and dried, weigh the washed and dried anode and record its new mass, which we are now calling X2 grams. So that's the whole experiment. That's the procedure. We began with a diagram. Then we went to the procedure. Finally, I want us to see the treatment of results. How do we treat the results of this experiment? We need to know mass of copper removed from anode, because the anode dissolved. It will be X1, which is the original mass of the anode, minus X2 grams. We need to know the quantity of charge. Which we call Q. It will be the amount of current we passed, which is I amperes, multiplied by the time you have passed that electric current through the system. So that will be IT coulombs. So this mass of copper is removed by this quantity of charge. And all that mass is the mass that's going to be deposited at the cathode. So we say X1 minus X2 grams of copper is dissolved by IT coulombs of charge. But we know that the equation that occurs is that the copper is dissolving to give us copper 2 ions. And that implies that according to this equation, it implies that 2 Faradays are required to dissolve 1 mole of copper. And 2 Faradays are 2 moles of electrons. 2 moles of electrons are required to dissolve 1 mole of copper. But before we interpret that equation, if this mass of copper is dissolved by IT coulombs of charge, how about 1 mole? In terms of mass, 1 mole of copper is 63.5 grams. You understand the comparison? Is dissolved by 63.5 times IT. We are cross multiplying over X1 minus X2, the whole of this in terms of coulombs of charge. So if these grams of copper are dissolved by IT coulombs, this mass, which is 1 mole, will be dissolved by this charge, quantity of charge. If I do cross multiply, this is now mathematics. Then the equation comes into play. In terms of the equation, we see that 2 moles, still the same mass, 63.5 grams of copper, is dissolved by 2 moles of electrons. This is 1 mole and 63.5. It is dissolved by 2 moles of electrons. What does that imply? That implies that 2 moles of electrons are equivalent. That's the mathematics here. These 2 moles of electrons, because they are depositing the same mass as this quantity of charge, so the 2 moles of electrons are equivalent to this quantity of charge. Are we together?
Yes, teacher.
So we shall say 2 moles of electrons have a charge of, that value we have already calculated, 63.5 times IT over X1 minus X2. coulombs. How about 1 mole? So 1 mole of electrons will give us the Faraday's constant. 1 mole of electrons has a charge of 1 times this over 2. That will be 63.5 times IT over 2 into x1 minus x2, the whole of this in coulombs. And that value of 63.5 IT over 2 into x1 minus x2 is equal to 96500 coulombs. It's approximately equal to that value, which is the Faraday constant. Let me hope the experiment is driven into your minds and you can describe it during your free time. Are we together? Okay. Now I want us to proceed to some calculations that involve Faraday's laws of electrolysis. And that's going to be our next subtopic.